Hello, everybody. Welcome to the front room. I'm your host, Nathan Rigoni. Today, we will be doing another paper review. It is Byte Latent Transformer, patches scale better than tokens. Today, we have a special guest, an old colleague of mine and friend, Jordan Conragan. He and I used to have a lot of talks like this over papers back when we worked a lot more together. I'm glad to have him back. And without further ado, we'll jump right into it. I'm just going to have you introduce yourself.
All right, yes. My name is Jordan Conragan. I'm currently a research engineer at 11 Labs right now. I was working on Scribe v2, which we've finally launched, and I'm really excited about that. And me and you, Nathan, used to work at Lockheed Martin together, and it was a lot of fun. And I'm really happy to be able to talk to you again about the same kind of AI stuff we were talking about back then.
But I mean, just as excited. You have no idea.
It's like the field has already moved so fast, and is so far from the 6 months ago when last we spoke.
Yeah, it's made a lot of jumps, and it seems like it not only has it jumped far in that period of time, it seems like the way that it's actually moving now, the things that are being changed are going to speed things up even more.
I agree. It's like we're at the very beginning of the recursive self-improvement loop, but it's not able to recursively self-improve quite yet.
Yeah, I think of and I don't want to like derail us from the paper that we're going to talk about, but one of the things that kind of convinces me that the recursive self loop is coming is how much better I have gotten as a programmer and coder and software engineer from the use of vibe coding. And it's not just that like I can go faster, it's that there were a lot of flaws that I had in my own skill set that are now fixed because models do a better job of doing that. Mostly documentation or even the callouts for things like variables as globals when they're called out multiple times in a script. That's just something I would forget to do, but now it's kind of fixed on its own.
And for me, it's the little small things I get from, let's say, forgetting to change a variable. I change, let's say, a string here and forget to change it later on, and typically something like a tab model will correct that for me just by itself.
True.
My own typing has probably caused more bugs than ideas or bad code.
Yeah, I would say me too. I don't know how many times I've run something, especially like a command in the command line that like for Docker and misspell the container name or something, and it just have to type it like 6 times.
I feel like we're getting derailed though already.
Yeah. Let's just move on. We'll go straight into the set of papers. You sent me 3 papers. The one that I think is kind of the meat and potatoes, probably because I'll say because it's the earliest one, is Byte Latent Transformers or Byte Latent Transformer. And then there are two other that are in there, and I'll name those 2. There is one from Goomball Lab that is the HNet, and then there is one that is Bolmo, which is bytefying the next generation of language models. But most of these or all of these have to do with attacking the tokenization problem. And I'm extremely excited about getting into that. So which paper would you want to start with?
So I think we should start with Byte Latent Transformer here because it's kind of the first of the bunch, and I think in a way it's also the simplest, although they all have to kind of deal with the same issues and they each approach it from a different perspective.
Yeah, I agree with that. And also Byte Latent Transformer I think it's the earliest one, so I think that's a really good starting point.
All right, and why don't we just get a few definitions out of the way first, because so many of our discussions just kind of come up because we have 2 different definitions of the same thing.
Yeah, 100%. Yeah. So one of the things I will say, like reading through, one of the things I struggled with early on was trying to understand why they called it like a byte pair encoding, or in this case, they're using byte latent. Can you describe for a second just like what that means as far as why they would use that word for their tokenization?
Sure. And in the case of, let's say, byte pairing, the way, which is a common tokenizer for a lot of different LLMs, it basically kind of learns from a corpus of what are the most common bytes, or basically like letters, and then one of the most common bigrams, and then one of the most common trigrams, by combining the previous ones and getting progressively larger and larger corporate vocabulary of words there. And it basically works on the byte level of you start with this byte that maybe represents A in Unicode, or in Hindi it could represent the pa symbol, which may actually even require multiple bytes. I don't know Unicode so well, but since there's so many different letters and characters and symbols out there, you can't fit them all into a single byte anymore. And
Yeah.
so
Okay.
byte pair encoding is its whole deal is that it works directly with bytes, and it basically combines bytes into a single token progressively.
Okay.
Whereas a byte level transformer does not have any of that combination. There's the vocabulary is pretty much just 0 to 255.
So it's basically down to just like the characters.
It's even kind of beyond the character level, because you have to think about Unicode and, let's say, emoji, or different languages like in different alphabets, which require, let's say, 2 bytes per character or 4 bytes per character, or however many bytes.
Okay. So the thing that gets me excited about going down to like the character level, at first, the thing that got me excited about character level is I always saw like character level encoding as the thing that gets us down past like the numerics problem, which is and for other people that might be a little bit more familiar with a different problem, it's the essentially the problem that is caused by or that causes the can't count the number of R's in strawberry. It's that tokens are larger than a character, and when you start asking character level questions to a large language model, it actually can't see characters. And this is really like what the problem is when you're talking about how does a model understand mathematics. It actually can't see per digit, and so there are a bunch of different ways that like the number 100,000 can be encoded based on how the tokens break down the digits of that number. And that was and hopefully isn't anymore a big problem in large language models. So this is what gets me excited in this paper. Tell us a little bit more about what they did here.
So basically, one of the big problems with byte level models, among several, is all of a sudden your sequence lengths. Actually, let's go with problem one. Your sequence lengths blow up. All of a sudden, and let's say I think Gemma Tokenizer has like 3.5 or 4 characters per token. Now, all of a sudden, if you have to do all those tokens in the byte level, basically your sequence length becomes 4 times as long. Or if you're training on the same amount of data, same amount of time, same amount of compute, you're training for 4 times less effective data. Like, imagine if you're able to train on 2 trillion tokens of text. Now you convert it to bytes with the same tokenizer, and it's either going to take 4 times longer, in which case you could have trained on 8 trillion tokens of the same text, or you have to only train it on 500 billion tokens, and you have a lot less data now to work with given the same compute. So what they kind of solve through that is they are patchifying it. So instead of just sending 1 byte is 1 token, they collect bytes into patches, basically, which is kind of like what a tokenizer does, but this is dynamic in the sense that based on the bytes before, it'll actually change the kind of collection or tokenization of the actual text and how many bytes get put into a single token there that the transformer sees.
Yeah, I think my favorite part of their approach actually might be that the patchwork, and it's because there are two things I really like about this. One being that they did this thing when I was reading the paper. I'd like to talk more about this. They looked at doing the patchwork based on entropy of the next character slash token, and that was really cool. But my favorite part of it is that there's now compression, and it's like a dynamic compression over a large section of tokens, or in this case, characters, so that you're not essentially trying to preserve tokens throughout, or large amounts of tokens throughout the entirety of the network. You're actually kind of detecting these like large patches that have different numbers of bits in them, which is kind of the thing I'm interested in. But yeah, like I dig the patches, man. I like it. It also handles that problem like you were talking about, where if you go by character, there's only so many characters you can fit in there before you're out of room, right? Like you're kind of trying to measure a beach by counting the grains of sand. Like it's just there's too many. Like we've got to group some of these together and we have to figure out how to do that. And their approach here is through entropy and patches, and I think that's really cool.
I absolutely agree with you. There have been byte models previously that just again worked one byte in, one token. And this is what I think was made byte level models really interesting to me, where all of a sudden, no, it's based off of the entropy of basically the next byte. And so if it's really easy to predict what's coming next, you can just throw that in the same token because there's not that many bits of information, so it could just fit into the hidden state.
Yeah.
But it's like you can only fit so much into a hidden state, and this kind of entropy based method seemed like a good way. Well, I say it's a good way. My only gripe is that you kind of have to tune that parameter manually.
Yeah. So
And it's
this
kind of
is
like
leading
non-intuitive.
this is leading into my first area where I want to kind of derail us, which is the fun part of like doing, paper talks. And also the fun part that you and I enjoy the most is I am obsessed with, as you well know, the bits per parameter metric and how it seems like to me, we are wasting tons of storage that could be taken advantage of inside of each parameter. To explain that a little bit further, each parameter technically is trained in a thing called floating point 32. And so there are 32 bits that are in the floating point, and we typically, with large language models from the last paper that was published on it, that at least that I read, are only using between 3 and 4 bits per parameter for storage, and there's so much more room in there that we could be storing things.
So that's the thing. I thought it was even like less, where it goes down into like 2 bits per parameter.
It does, and I'm just talking about the average. There's a large amount of variance between them. To the point, there are other points I would make about what's happening in large language models beyond that. But let's jump back to let's jump back to the paper we're supposed to be talking about.
We'll jump back to this. So the meta paper basically works by taking in bytes or characters as the input, using a entropy based chunker to say, all right, next token low entropy, next character low entropy, put that onto the same token, next token higher entropy. So chunk that, stop that barrier, take all the low entropy characters, put it into one token, and so on and so forth. And so all of a sudden, you're not the number of tokens is less dependent on the number of characters in there as it is the amount of information in there. So, and that corresponds to how much compute it gets. So, like a super low information sequence and that's super long and a high information that's short, like a high information dense sequence, may get the same number of tokens. At least in theory here. I think in practice it's
Yeah.
not as good, but that's what I love about all these patchifying tokenizers here, is that you can essentially allocate the same amount of compute for the same information density, not the same, or not density, but the same amount of information in a sequence instead of just the length of the sequence. And I love that. I think that's kind of the way we want to be going.
Yeah, totally agree.
Plus, it also encodes the information of the characters, which is kind of a silly thing not to do for language models.
Yeah, I think, yeah, going down to the character level, I kind of felt like that was the place we needed to be. I didn't know that it was going to be a solution like this. This is extremely elegant. But thinking more towards that problem of like numerics, like the patchification of a numeric expression, something that's like, multiple digits long, I think that's awesome. Like, I can't wait. Honestly, I can't wait until there's like an open source model that's like one of these that I can mess around with, because I think these are going to be so much better at math. They're not going to have the same pitfalls that a lot of the current models have, and probably a better user experience.
Well, I do have good news for you there, Nathan. Meta did open source one of their Byte Latent Transformers.
Wow. Okay. I've got to test it.
And everything that Allen AI does is open source. So Bolmo is also open source.
Okay, I'm gonna test both of those. I'm gonna add them both to my VLLM library, and I'll load them up.
And I want to talk briefly about the math. I totally agree that math tokenization, the way we tokenize numbers, harms math performance. But on the other hand, I think at this point we've added so much math into the training data sets for these models, and some of these models are getting big enough that it is able to semantically understand what those tokens mean in the same way, let's say, Claude understands, has the same like latent vector uh, for the different concepts in, or the same concept in different languages or different phrasings of it.
Oh yeah, totally. I totally agree with that. The issue I guess I'm talking about is that there's a scale issue with that. So for things that are like very commonly used numbers, like if you were to make like a distribution of like which sets of numbers are commonly seen together, it's gonna be like things less than 9 digits are seen more than things less than 14 digits. The higher the number of digits, the less it's going to have appeared in the training data. And because of that, there's going to be this lack of understanding as the digits get longer as to what that number likely means. And so now, because we can look at it at the character level, there's going to be almost like a built-in understanding of the characters themselves, even if we are patching it, so that whenever you get out of sample and you extend the length of the digits in a number, the the model will be more likely to be able to perform well in that out of sample space.
I hope that's the case because in like different papers, I think one of them from Cohere about how LLMs do math. Well, in a sense, it's kind of like how I do math. It's a big bag of heuristics where they don't they don't follow math like a calculator does and follow
Right.
that algorithm. They kind of just add stuff in their head and fudge numbers like amazingly very much like how I would, and
Yeah.
also like how I would. It breaks down at higher numbers of digits. I am very much like an LLM in the sense that you give me too many digits and I'm not going to be able to just do it.
Yeah, I've gotten to the
But
point now where I'm so dependent on a calculator that my max number of digits is 2. Like if you give me a number beyond 2 digits, I'm like, okay, all right, we're just gonna sit down with some paper. I might I might pull out my phone.
I think at this point LLMs are good enough, are better than me at math in their head. In fact,
Yeah.
I know it because I've given them questions, and then there's better. But then it goes into all right. When it comes down to it, am I better at applying the algorithm for, let's say, multiplication to very very long numbers better than an LLM can? Will I be able to maintain coherency and accuracy over the steps of an algorithm longer than the LLM can? And I think still could, maybe not against some of the frontier LLMs though, because how many times have you heard the phrase, "Oh, I forgot to carry the one"?
Oh, yeah.
Like that is literally just that is equivalent of an LLM making a mistake
Yeah.
in the middle of a mathematical computation as it's trying to say carry out the steps chain of thought wise. It's just us forgetting to carry the one. So I actually don't know if I could beat some of these frontier LLMs in a head-to-head algorithmic following competition over long steps. But for some stuff, I still got them, like Pokemon.
Totally agree. Yeah, so before we move on to Bolmo, is there
Mhm.
anything else that we didn't cover in this paper that you found interesting?
Just some of the challenges with this. So one of the problems with the byte latent transformer is that they essentially have to train a submodel that is working byte in, byte out, kind of no patching to calculate the entropy of the sequence. Like in a sense, that's almost equivalent to like training a tokenizer for the other model, but it's like you're training an entropy tokenizer in a sense. So that's
Yeah.
one problem.
Yeah, I could see
That
that being difficult to kind of conceptualize. How do you solve that?
it's not even so much that it's so difficult. It's basically just the same byte level models from old. The fact of the matter is, though, you still have a separate tokenization and model training step, as opposed to being able to like combine the two of them.
Yeah, so that's a good point. That's a good point. So that's something that actually came up with my own home experiment with the convolutional compression of tokens. And it because I'm doing two separate trainings, right, with two separate goals in mind, and I was having to freeze the autoencoder for the encoder decoder for the tokens into that embedding space. And I gotta say, like, while it is annoying that you have to train two separate things, I sometimes think like maybe that's not a problem. Like maybe that's the appropriate way to do things.
Well, in my opinion, the kind of less bias you can put into the system, especially let's say for the massive trillion number of tokens when you're training on. Like the amazing part of a transformer is you just give it data and it'll figure out a very optimal solution at scale.
Yeah,
So maybe doing that training first doesn't lead to the optimal entropy
that's true.
chunking model.
Yeah, it's a trade-off, right? Like you are keeping it isolated and independent, but it may not be the most efficient solution for predicting the next concept or token or word. Okay, so I
So
guess we can transition over to Bolmo if you want. I
could,
didn't
could we
actually get
actually
a chance to read this paper, but I glanced over it. So,
Could we actually go over to HNet because I've
oh
spent a
yeah,
bit more
sure. Let's
time
go. Let's
reading
go to
that.
HNet first.
So HNet, by Albert Gu and his one of his PhD students, and he's one of the same guys who made Flash Attention and Mamba.
Oh, cool.
So same group, they're awesome stuff. They basically everything he's touched is pretty darn cool.
That's a pretty good
And
review coming from you.
if yeah, I follow his lab and whatever comes out of it.
Okay, so can you give us like a brief synopsis of the paper?
Yes, so HNet is it stands for hierarchical net, but the actual paper name is like dynamic chunking for end-to-end hierarchical sequence modeling. And all those words basically mean it's a byte level model, which means bytes in and bytes out, and it uses dynamic chunking, as in based off of the bytes themselves, they get combined into tokens that is processed by the I say transformer, but the main sequence modeling model with all the most of the parameters in it.
Right, like the
And
typical LLM part.
right, the typical LLM part. And now they found that using an SSM like Mamba was better at it for because Mamba I guess has a learned compression
Okay.
aspect to it
Yeah.
versus transformers can almost cheat by looking up the next to previous tokens, but more or less tokens in, tokens out. Oh, sorry, bytes in, bytes out, and a dynamic chunking method that chunks bytes into a single token, kind of based off of. In this case, it's a learned method. I haven't even fully figured out how it works,
Okay.
uh, but it is not too dissimilar from the fact of it compares when there's enough change from the previous tokens.
Okay. So it's like using a drift model almost.
I, yes, but it's like a learned routing module, if you will.
I gotcha. But this is the major difference that we're describing here, like this dynamic chunking, to bring it back to similar terms as the previous paper, this is their way of doing patching. Like the previous model used entropy for the next token to decide when should I break into the next patch, and this one is using a dynamic chunking algorithm to decide how to patch the bytes.
It's not so much a dynamic chunking algorithm. It's a part of the model that I guess it is also an algorithm, but part of the model that learns during training here. So it's not a separate model, no
Oh,
separate
okay.
training.
So we're not
Uh,
pre-training in this one. We're just going straight into it.
exactly. It's just straight up starting from scratch. The routing module doesn't know how to chunk text semantically at first, but then afterwards they have a super great animation on the GitHub. It learns pretty. It learns at the end of training how to chunk stuff, like
That's
based
pretty
off
cool.
of words or semantics, and you get some similar stuff to tokens, but it's not necessarily the same tokens as you get in English text.
Gotcha. So it's almost like finding out what the and actually this is extremely interesting. So with this model, you could potentially use it to analyze some language from like a linguist perspective to be like, what are the common chunks that actually lead to the meaning in the sentence or in the paragraph, how you chunk this up. Like it might identify better roots than what they did with like the GPT-2 tokenizer. It was essentially just looking at bigram.
Right, right, based off of frequency.
Yeah. So this could pull
I,
like root words out almost.
in a way, yes, but of course we also have to think about what is it being optimized for, and in
That's
this
true.
case, next token prediction. So this is like it learns what are the best chunks for next token prediction.
Yeah. Yeah.
Um,
Interesting.
so the other really cool part about this is that it doesn't have to work just on tokens. Like that's
Oh,
the other thing. It's hierarchical because they apply this routing mechanism maybe two times and two or three times to downsample like two or three different times.
wow. Okay.
So not only do you, it basically may go through multiple passes where, let's say you start with 1,000 tokens, it's 1,000 bytes. It goes through this, you get to like 700 bytes, and then may go through the layer again to get to 500 tokens.
Okay. So it's almost
So
like so it's downsampling as it's going through there.
yeah, downsamples, and you can downsample arbitrarily because it works on vectors and it just works on the byte embeddings.
Oh, so this actually this is seems related to another concept, sort of that I've thought about, which led me to the token compression piece, which was our language, like especially English, let me say, is very inefficient. We don't use a very efficient language. We typically like focus on things like poetics and things like that, and how we add these extra words for not necessarily the meaning of the thing that we want to get next or the meaning of the sentence that we're trying to convey. We add a lot of words in there that make our language flowery, and we also add a lot of words in there that help convey other senses to other people. Things like propriety and like introductions and the please and thank you of language. And I have thought a few times, like, wouldn't it be easier for a machine who doesn't really care about that as much to be able to translate what we're saying in English or in whatever language into a language that it's much easier for it to compute. This was one of the reasons that I thought, like I made the argument earlier about like maybe pre-training the autoencoder is the right way, but from this paper and what you're saying, this is doing that, and it's doing it in the same process as predicting the next token.
Yes. Now, to your point, we would, when it comes to like let's say translation there, we would need to have no, actually no, I see what you mean now. Where this in a sense, these downsampling layers compresses it in a learned way that helps it do whatever task it's trying to do.
Yeah.
I think because it has to predict the next token, it's compressing it in a way that helps it predict the next token. So it has to know, it has to be able to do the flowery language because there is flowery language in the next token.
Yeah, of course, of course.
But say we gave it a different task altogether that's not just predicting the next token of English text. I don't have a good example off the top of my head, but it may be able to organize and downsample the English language we give it into a representation that is best for it to do that objective.
Yeah, much more efficient. So even with the flowery language of like predicting the next token, if it's downsampling there, that means that there's some inefficiency in the language. I don't want to like I need to reread the paper that we were talking about earlier, but this to me is like this seems to like justify like that tokens aren't the most efficient storage of information. Like they're inefficient and probably like some kind of low bit rate, and it's the combination of tokens that create information. Uh, I really think like that the compression thing, especially with now that you're talking about this paper, I think compression's the way to go. Like we really need to start compressing things. We're the way that we're doing it, where we're preserving tokens across like the entirety of the network instead of compressing down to concepts or contexts. I think that's a big inefficiency that we could likely solve and reduce the size of models.
Okay, I want to say two things here. One, you've basically come to the exact same realization that Albert Gu, the author of HNet, came to in his blog post. Like
Oh,
that's
nice.
almost like what he's saying is compression is the essence of intelligence.
Yep.
And you realizing that on the podcast basically just sped run that entire journey he
Nice.
was going through.
Well, perfect.
And secondly, the other thing about tokens being inefficient, I agree. And again, same thing in that blog post when he was talking about HNet. He mentioned that HNet is also a form of like multi-token prediction because in the end you have one token that goes through the sequence model, but it turns out to be multiple tokens at the end.
Yeah,
And
that's
he's
the decoder.
argues that just the fact that models can do multi-token prediction with tokens means there's a certain amount of information density that means some tokens are just really information light and inefficient because you can just predict two tokens at once from the same hidden states.
As an example, I would use the word and. I feel like the word and probably gets tokenized together, either by patch or by selection of like GPT-2 because it's only 3 characters, but it is a very light information token. Like it doesn't carry a ton of information. It just means that like the Senate, like there's more information coming. That's all. It's just a precursor to more information coming down the pipeline.
Oh, that would be a fun instance to see how often, or like how much information each word has based off of like
Yeah. I bet
how
you, I
much.
bet
But
you it'd be highly correlated with the entropy in that patchwork.
I want to say one more thing,
Go ahead.
and that is something like and may still have high entropy because think about what at the very beginning of a list.
That's true.
I like burritos. There's a lot of different possibilities after I like burritos. It could be just a period. It could be or. It could be a comma. It could be and. It could. There's a lot of different possibilities, and so and is going to be maybe a less probable token, and that's when let's say the byte latent the meta model would chunk it right there because
That's
it
true.
does
That
well it
is,
would chunk
yeah.
before and oh but maybe what you're saying is once it has and well no because even once it has and it may still chunk because it doesn't necessarily know what's coming after it
Yep. I
so
guess that was
and
my point though, is like the information that you gain isn't from the word and. The word and only has so much information in it, essentially saying that we're going to continue to some extent. And then the thing that comes after and is the thing that adds more information.
I totally agree with you there but not, the more I think about it the more I go well maybe they do chunk you chunk around and because those are high very high uncertainty and you
Yeah.
don't know whether what you before you say the word and you don't know if it's going to be and after you say the word and you don't know what it's going to necessarily be so then how I guess that's the tricky part about autoregressive stuff if this was a bidirectional model I bet and would almost always be tokenized in with something else
Yeah, it would just be clipped in to something.
it, but
Yep.
since this is not bidirectional since we're doing it autoregressively I think that's why and it's like when um it's the aha moment from DeepSeek, or where a lot of GRPO papers focus on the words like although or but maybe because those words are like inflections where after that there's a low probability of like 10 different things happening.
Yeah. Yeah, that's a good point. See, this is why I like thinking about this stuff. This is why I like having these discussions with you. It brings up this kind of thing. So do we want to move to the last paper?
Yes, and that's the thing. I haven't read Bolmo very much, but I think I wanted to cover Bolmo, HNet before Bolmo because it is very similar.
Okay.
Bolmo by Alan AI came out with Olmo 3 like December 2025. Also, Alan AI, another great research organization. And it has a somewhat similar thing where it's like you have the bytes as input, a learned chunker that learns as you're training the model, your sequence model, in this case a transformer, and then the decoder part of that too. And I don't think it quite works as well as HNet from the hierarchical stance. I don't think you can chain the uh, tokenizer or patchifier or however you want to call that.
Right. It looked a lot more similar to the first to the byte transformer to me, with the exception of in this particular instance, they're instead of using like a cross attention mechanism to get the patches, they're using an LSTM.
It's an LSTM, but I want to talk about the other really crazy thing is that they look ahead as they are chunking with the
How do
LSTM.
they do that?
At a high level, looking at the blog post here, the Bolmo boundary predictor is non-causal,
Okay.
basically meaning during the pre-training, it just figures out uh where to chunk non-causally. So if you're in the middle of a word, it may look a few a few bytes to the end of the word to see whether it should chunk that word or not.
Gotcha. Okay.
And then I think during inference, it naturally happens so that it generates the whole word or the whole kind of important bit. So even though the chunking is non causal, during generation, it'll be generating the kind of patches that it would expect to see.
Okay.
Basically, it's said in the same way that tokenization training is non-causal because you know the whole word
Right. Yeah.
and you
You're just looking at how to split it.
exactly. So in this case, the boundary prediction is non-causal, but it looks like there's still the LSTM that embeds the whole token or that chunk is causal, so you don't have contamination.
Gotcha. But
But
overall, from like a higher from a higher level, this is a very, very similar approach, at least it seems to me, to the byte transformer.
yes, in a sense, you have the boundary predictor. You have a way to convert the each chunk to a single token. You send it into the LLM, and then you have a way to decode it. And I think the really cool advancement from Bolmo here was that they tried to make it really easy to take an existing LLM based off of byte pair encoding or other subword stuff and make it basically adapt it for byte.
I gotcha.
So you could take a llama model and make it a byte model using their method with very little compute.
Okay. I kind of want to ask some more questions that are a bit deeper about all of these. One of the things that interests me, or at least the predictions on like where artificial intelligence is going with many of these models, is I feel like it's going smaller and faster. Like we're increasing efficiency, we're increasing the accessibility of these models because we're no longer at the point where we were when we were moving from GPT, 3 to GPT 4, where, and even when they started introducing Grok and, everybody started coming into the game where we're talking about trillions of parameters on these models. Don't get me wrong, they're still scaling up. But the performance of the smaller models and the performance gains that you get from things like this do mean that we can have something that's much more accessible and much more performant on a smaller GPU like hardware footprint.
Absolutely. That's been so cool. I think that's also part of the fact that distilling is a lot easier than training from scratch.
Yes, 100%. I guess the one of the questions I want to ask you, just as a now that we're into the opinion piece of this, one of the questions I want to ask you is, when do you think we're going to stop being able to quantize? Like, if we can move to like a place where we start getting like bigger and bigger patches, like I almost see like between the HNet and between the byte transformer, like if we can somehow move to a place where those two things come together, that we might be able to move to extremely efficient storage of information and parameters so that we are getting up towards that like 32 bits, right? And then we won't be able to do things like quantization on these models because that will effectively destroy their performance. So my question to you is like, how long until we get there, Jordan? Okay, like that's the place I want to be.
Well, okay, that's the thing. It seems to be so dependent on the model architecture itself. Like, let's say Mamba,
Yeah.
very sensitive to quantization in a few of its operations. It can't be. It has to be like float 32
Wow. Okay.
versus, let's say, FP8 for linear layers can be in like where it works, or and the 4-bit floating point. Heck, bitnet -1, 0, or 1
Yeah.
seems to work somewhat well for linear layers, and I think in part of that is because we aren't able to utilize, as you're saying, all the parameters that we have like efficiently. And I don't think that's even a data thing. I think that's how we train with gradient descent and how we and the parameter of the network itself. And I think okay, maybe in the next podcast here we go through the physics of language models and discuss exactly how it worked so that we're not saying wrong things on the podcast here.
I
Because
totally
I
agree. I
thought
totally agree.
there was one more thing then I wanted to talk about tokenization here.
Yeah, go for
And
it.
then we talked briefly about how many R's are there in Strawberry.
Yes.
I think I have the human equivalent of that, or kind of know that.
Oh, that's perfect.
And before I go into this, though, I want to hear what do you think the equivalent of tokenization is for humans? I want to say not just the equivalent, but an equivalent. It doesn't have to be comprehensive, just something.
An equivalent. I think an equivalent of tokenization, in my mind, what I like to compare it to is group counting. I don't know if I don't know how many people will be familiar with this, but like when you're a child, you can't group count. It's not a function that you have. Like you have to learn how to do that. So when you give a child, like that's why you start with a like a baby or a toddler. You start counting with them, like 1, 2, 3, 4, 5, all the way up to the number of things that you've given them, like to 10 or something like that. But as they get older, they start to learn to count by groups. So you can do things like they can look at a series of 5 objects and automatically know that there's 5. And in a way, what they're doing is they're tokenizing the objects. They're grouping them together so that they can count by fives or by 3 or by whatever. That's the way I've often thought of tokenization, is like we're grouping things together so that we can contextually provide some meaning for that group, and we're sort of counting by grouping.
All right, I hear what you're saying there. I kind of put that more into the realm of learning skills, uh,
That's true.
and like how not as much tokenization where a model doesn't learn induction heads for a little while. Maybe group counting is like an induction head for an LLM or copying. So then, the way I kind of look at it is like the human eye seeing colors. And
Okay.
you know how you have rods and cones in your eye, and you have like a gosh, I'm actually gonna have to look this up because it's been
That
my elementary
yeah.
science class.
I see where you're going with this though, and I think that's another good point.
And basically how your photoreceptors in your cones detect like green, yellow, and something else, blue, green, yellow,
Is it
red,
red?
and then in any case they detect 3 colors, and then it's the combination of that activation that tells your brain color. All right,
Right. Yeah. Why don't we just
and
see the world in 3 colors, right? Your brain
exactly
is
why.
putting that story together.
Exactly. So your brain takes the activate, and don't even get me started on the fact that color is just the light that doesn't get reflected,
Yeah.
or the wavelength of light. That's a whole nother thing.
Yeah.
And honestly, I'm not by the fact I don't remember which colors our cones see. I should not be the one that you should listen to about color theory itself.
We
But
aren't
all right, we have.
biologists.
But okay, you have your say red, blue, green cones, and each of those gets activated a certain amount whenever you're looking at any object. And
Mhm.
it's the combination of those three that your brain interprets as a single color.
Yeah.
But
It,
imagine it's like counting the number of R's in strawberry is like looking at something for me and identifying how much your red cell is being activated. You look at, say, an orange and you say, how much red is that being activated?
yeah, it seems like a ridiculous question. Yeah.
It seems like a ridiculous question, and yet there are people who could do that or something like that.
Yeah,
Case in,
that's true.
case in point, my great grandfather did painting and lithography for a fruit company.
Okay.
And basically, what that means is, yeah, I think the technical term is lithography.
That's painting
Right,
letters, right?
it's more like printing onto a thing, I believe.
Okay.
With a big plate, and this is way back in the uh 40s. Yeah, it'd have to be back in the 40s and 50s here in San Francisco.
Okay.
And one of his jobs was to basically make the plates for the printing so that it'd be basically printed onto the box of these for the fruit. And he would A, kind of draw out the design, and then B, make the plates for it. And he would have basically the three basic colors, the cyan, the magenta, and the yellow. And it would be his job to figure out how much of each color gets added onto each part of the plate to make the photo that he was looking for.
Oh,
So
okay.
he would actually be able to say there's this much cyan, this much magenta, and this much yellow in this color point right here on the reference picture.
Oh, so like it's kind of like so he had to do some process that was similar to what they had to do when they started color newspapers, where they had to figure out like because a newspaper is printed in dots. And so it's like the dot matrix printer for producing colors when all you have is cyan, magenta, and yellow.
Right, and essentially you'd have to figure out how much of each color do you need to add to make that particular output color.
Yeah, to fool
And
people into thinking that they're seeing green.
exactly. And so that's the kind of stuff where I think, okay, if the basics of anatomy is you see the three colors, those are the three things that get activated. Those are essentially the characters, but your brain combines them into the embedding vector that our brain actually receives. But
gotcha.
someone like my great grandfather or anyone who does any of this sort of stuff could see a color and break it down into its component colors and how much it activated. And in that case, he was working with different colors than the brain was activating on, but in theory, you could also replace whatever the magenta, cyan, yellow with those three basic colors that the brain activates. And you could say, no, this is activating 50% of my red cones, it's my blue cone is 38% activated, and my yellow cone is this percent activated.
I think that's I think that's a really good analogy. I think your analogy is way better than mine.
And so just like how the number of R's in strawberry is a solvable problem for LLMs, like they're getting it.
Yep.
It is the same thing for humans, but you need to be. He was trained to do that kind of stuff, and it took a lot of practice. And I don't think just anyone could do it for biological reasons, and also just the fact that everyone has different skill sets. But
yeah, totally agree.
But it's like with LLMs, you're able to train a model to count the number of R's in strawberry. You just have to actively train it for that.
Yeah, that's awesome, man. Thank you for sharing that. Jordan, I'd like to thank you for coming on and sharing these papers with us, and also sharing some of your insights. We really appreciate it. Thank you.
You're very welcome, Nathan. I was very happy to be here.
You've been listening to The Front Room. The Front Room is written, recorded, and produced by me, Nathan Rigoni. If you'd like to know more about what our company does and what it could possibly do for you, you can reach us at nathan.rigoni@phronesis-analytics.com. We'd like to thank you for listening, and have a good day.